So we are very fortunate to have Vladan Vuletic giving our coupon seminar today. So my main challenge for today is to give a different introduction from the one Monica gave yesterday. So I think the place to start here is Vladan received his bachelor's from LMU in Munich, did his PhD there as well, working with the Red Devil lithium. That's not Ted Hench. He was a postdoc here at MIT, working on manipulation of seed. Sorry. And developing general Raman sideband pooling and the best stop resonance techniques that led to cesium VDC. He was actually faculty here at Stanford in Monica's office before moving to MIT. Two most important years of his career, 2004, the year I joined his group, 2005, year Monica. So by way of a little bit of history for you, I was trying to figure out what I wanted to do for my PhD, and I went to Hideo Noguchi's office, who was then faculty at Caltech. And I asked him if I was going to do AMO, who should I work for? And I remember to this day that what he said was that Vladan was the poster child for atomic physics, and that if there was any way I could work for him, I should. And I took his advice. So as you'll see today, he's really a uniquely creative scientist, both in terms of kind of the day-to-day, that anything you need to do, any problem can be solved if you're willing to relax your assumptions about what the rules of the game are enough. And in terms of kind of big picture questions about synthesis of new directions. And so the last thing I wanted to say is that while I can't really tell you where that creativity comes from, I can tell you that one of the big things I took from my PhD with him was that he insists on building simple, intuitive stories about how things work that are connected to some kind of a formal theory that tells you where those ideas apply. And I feel like that's both the only way to layer complexity to build more and more complicated systems and solve harder and harder problems, and also that these simple stories are really fundamentally the product of our science, more than quantum technology, more than nature papers, believe it or not. The contribution to understanding is simple pictures that you can layer. So with that in mind, and hopefully without putting too much pressure on Vladan, I hope you enjoyed his talk on quantum mechanics.
All the faculty out there, get your good skills early. That helps a lot. So today I would like to tell you about enhanced quantum metrology. This work was several projects led by Seyan, who see an audience, who's in our postdoc, working with John on various interesting extensions microwave. So basically, I would like to tell you what the super standard quantum limit is. One standard quantum limit measurement, which is not really a limit in the sense that it's only a limit if you use undependent particles, but it's overcome by entanglement, and how we apply it to try to improve the world's most precise instruments, which are really optical transition. These clocks, as you may know, from years of the folder, reach this mind-boggling stability around 90 digits. So they are so precise that measure time from the Big Bang, it will be less than 100 milliseconds or something narrow. And they are by the best instruments, and we're trying to make them even slightly better than the so I would like to tell you about the spin squeeze talk. Spin squeezing, if you don't know what percent limit. And then particularly focus on the technique that was invented here at Stanford. A very nice paper by Monica collaborators, which you can use. There are different names for this technique, like we call it time reversal based quantum metrology. It's basically the idea that you have a many-body Hamiltonian that makes an entangled state, and you are able to switch the sign of the many-body Hamiltonian minus h, then because of the unitary evolution, it's equivalent to a switch the sign times. Time, of course, doesn't run backwards, but if you have a negative Hamiltonian, then you can involve the system backwards. For quantum measurement. And then I would like to finally focus a little bit on this idea that maybe you can use a much larger variety of Hamiltonians than the ones we've used so far. Connection these to make measurements better for entanglement and also maybe to elucidate what I think is the deep relation spreading quantum information. So let me tell you what this is all about. So all the best measurements are quantum measurements. They are basically going back to a two-level system. We label the states 1 and 2, and we are trying to measure the energy between. And this applies both to clocks and to other systems. So if you want to measure its magnetic field or electric field, then we try to make the energy proportional to the electric or magnetic field that you want to measure. On the other hand, if you're trying to measure time, then you would like the energy to depend on nothing that varies in the lab. And then you basically use the phase evolution speed, E over h bar in a quantum system, as a measurement of time or as a peak rate. But as I said, this applies to many different possible measurements. And so if you create this proposition of states 1 and 2, and then you try to measure the relative quantum phase 1 and 2, which involves this frequency over h bar. We cannot measure phase directly, but you can do a rotation in this spin space where you map the phase of the population difference between levels. And for the non-experts, we like to describe this as sort of log sphere. So you can think of this sphere as describing the system of either one atom or n atoms, where say all atoms in the lower state spin down, all atoms spin up, and then any state along the equator state some phase that's defined by the direction. And then a very nice way to visualize quantum noise comes from this noise that is there even in all technical source of noise. Is formally you take channel and spin 1/2. They're all doing this, you add up all the things to a large spin. The atoms are in the ideal case all doing the very same thing. The spin are pointing always in the same direction. And therefore you live on this larger velocity, which is really a large spin or large angular momentum. And this angular momentum is a quantum mechanical angular momentum, the base quantum mechanical Heisenberg relations, mutation rules. And so that basically means that unlike classical angular momentum, it point perfectly in one direction. The quantum angular momentum always has some uncertainties, which is given by the Heisenberg relations. And this corresponds to a certain fuzziness of the vector, so it never points perfectly in one direction, but transversely or an uncertainty in angle goes as 1 over the square root of the spin, 1 over the square root of the total atom. And this is what we refer as the standard quantum fact, trying to measure the direction, phase evolution of this system. We cannot do it. And so we usually work with so-called Ramsey sequences. So the idea is here we start with the atoms in one of the quantum states. Then we apply the 2 pulse proposition, which is the 1/2 atom, and then it's one equator along some direction that's given by the field that you apply, it's local phase, and then basically you let the atom evolve, also surface speed, the energy difference between the 2 states, and you compare that to some block. This is the laser pulse and optical transition, and we compare this atomic phase to the phase of the laser oscillating. And so the system evolves, and finally you try to bring out the atomic phase relative to your laser, because you use to stabilize your laser, and to convert this phase into a population difference, you do a over to the x-axis, which converts this phase that has been accumulated in population difference that has been accumulated, and you try to measure this, and as you see, this fuzziness here is really coming from the Heisenberg uncertainty relations that indicates that you cannot measure the phase in single shot. And this fuzziness, of course, remember undergraduate quantum mechanics as delta S5 times delta SC, the 2 orthogonal directions, mean directions of spinning are given by this Heisenberg relation, and this is something you cannot violate. However, in the normal situations, by symmetry, delta S5 and delta SC are the same. However, Heisenberg uncertainty does allow you in principle to, as long as you retain this product, make one of the uncertainties smaller, say in the y direction, or x direction, at the expense of the other component. And so if you imagine that you somehow, by maintaining the area of the uncertainty, squeeze, say, the phase direction, then you can already visually see now I should be able to measure phase. And this is called spin squeezing or spin noise squeezing. And if you think about it, this system on the left is a not entangled state, so this is just the product state of each atom being in the same superposition of spin levels. The state on the right is necessarily entangled. And so basically for this concept has been known for a long time, but people didn't really know how can you make a state, say 10,000, 1,000 or 1,000,000 particles that has entanglement built in this. But the moment that you had that, then basically you squeeze the noise, squeeze the noise, then you let it evolve. You can see it's narrow in the phase direction. After a final rotation, this narrowness in the phase direction becomes lower noise in SD, which is what you measure. So you can see that you expect that value mountains. So now the left atomic clocks and atomic parameters are at this limit or very near this sort of standard quantum limit. This is where the precision proofs at the numbers and half. I've described this as coming from quantum mechanical uncertainty relations, but you can also think of this as just points. So in the superposition states, equal probability of up and down. It's like throwing coins, and if you have 100 coins and you throw them on average, 50 will be pointing up and 50 will be pointing down, but of course you'll have noise from that, but only on one. So another way to think about it, it's really coming from the discretization of the measure. The fact that when we try to measure spin, we always get only a result without each atom, never any. So these are pictures like equivalent, but many body entanglement used to overcome the standard quantum limit. Spin squeezing is the simplest version, but I will show you that other versions possible as well to use. And so, what is the simplest possible Hamiltonian to make spin squeezing? Well, if you think of the very simplest possible Hamiltonian HSC, then of course we all know what that is. That is just rotation of the z-axis by theta. How long you apply the Hamiltonian, so that will preserve the state, will just rotate it. But as soon as we make this Hamiltonian SC squared, then you can think of this is an SC dependent rotation. So basically, state of the rotation, say above the equator, faster than at the equator, and is a little bit faster than below the equator. And so you can see that that shears the state. In the system, and this was known since Kitawa and Veda in 1993 in the seminal paper. This paper was published in PRA. It was turned down by PRL, because it was not relevant. And also in their paper, they said this is the Hamiltonian, but we have no idea how to do it. Right? Because this Hamiltonian ultimately requires all-to-all interaction in a many body system, right? How do you do it? So it took a while for experimentalists to start thinking of or start figuring out how this works. And so there are actually two ways. One is done here also, for instance, the Markasevich group and James Thompson group, and we did it also early on in Monica's PhD, which is you can use a weak method. So if you try to measure SC, but you don't make the paradigmatic quantum mechanical thing where we try to measure so that we project completely, but you can make a measurement that narrows down your uncertainty on SC. It turns out that it's squeezed. And this is what we did first. And then at some point I said to Monica, can you please look at our cavity interaction and see whether we can make this SC squared Hamiltonian? I have a feeling it won't be possible. I have no idea how to do it. And then the next day, Monica came back the next morning, all excited. She led me to the whiteboard and said, this is how you do it. So I don't know whether she figured it out in 5 minutes or did sleep that night, but she had an idea. So basically there's a way to do an SC squared Hamiltonian that we like to do, which is to use light atom interaction in cavity. And there the idea is that all the spins, all the atoms coupled with photons in the cavity, they can exchange virtual photons, or another way to think about atoms in the cavity, lights, the state of light in the cavity, and that state of light is what you have to see by all the atoms. And that's how you get an effective atom interaction where any atom is to any other atom. So applied to clocks, this is schematically what our experiment looks like. we have a cavity in the vertical direction for the exposure is even with the so-called strong single atom coupling limit of the cooperativity of anywhere between few and maybe 10 or so. But what we really need for spin squeezing is a product of the coupling strength of all atoms and single atom cooperativity. We have a clock laser in the transverse direction, in order not to have any Doppler effects from the clock laser. That's hold and trapped, but they're still moving around. We use an optical lattice to have the atoms sort of lambda regime. Basically, the atoms are prevented from moving over a wavelength, then we won't see a Doppler effect. And then to have long propagation times, these atoms are trapped in lasers. And this was a big invention of Tori's group, who basically proposed to use trapped atoms in such a way that the ground state and the excited state of your transition experience exactly the same variability, exactly the same direction. And so then you can probe the atoms as if they were in free space, even though. By the way, maybe it's interesting. Tori actually thought of this first when he thought about how to build a quantum computer, how to build spin systems that you could control, but this. And then it was applied to clocks. And this shows you maybe that there's a very, very close relationship between running with clocks, running, say, quantum simulation computers, because the requirements of coherence and so on are largely quite similar. So maybe first a less formal view of how this works. We have terbium, which is 2 nuclear spins minus 1/2 and 1/2. We apply a magnetic field, so we split out excited state 1. This is state moderate line with about 100 kilohertz. We split the levels out so that this transition indicated here 1/2, 3/2 circularly porous line is approximately, certainly a closed transition, approximately isolated from the other transitions. And then you park the cavity on this transition and put atoms inside it. And then, as many of you know, what happens is the atomic 2-level system and the cavity will hybridize, and they form this vacuum-Rabi splitting. Another way to think about the case on resonance, there's a lot of absorption from the atoms, but then away from resonance, there's going to be dispersion from the atoms. So we get this vacuum-Rabi split. This vacuum-Rabi splitting depends on the number of atoms in 1/2 state. Basically, the square root of n, there are more atoms that can Rabi state. And then this is what Monica figured out. If we park the laser on the slope of the cavity line like so, and then imagine that we have quantum noise in this system. And basically, if we have more atoms to quantum noises in state 1/2, then basically the vacuum-Rabi splitting will be bigger. That means the laser that we park there in the slope will be closer to the resonance. So we'll have more light inside the cavity. And now the light inside the cavity acts back onto the atoms. Produces a light shift, and because there's more light in the cavity, there's more light shift and more noise. And similarly, if the laser, the atom number is smaller in the state 1/2, then the mode splitting shrinks, the laser is further away from cavity resonance, there's less light and less phasing. And so in this way, mediated by photons get an effect where the atomic SZ, the fluctuations in the population difference, basically correlate with the atomic SY or the phase evolution to give you effectively the SZ square. So if you want to think a little bit more formally about it, this is the Hamiltonian that we're working with. It has 3 terms. The first term, C dagger C, is the photon number inside the cavity. That's simply the energy of the photons in the cavity. The last term is simply the atomic energy, which for omega A is the splitting between atomic energy levels, and the C tells you just how many atoms stand up at lower state. So that term is just the atomic energy, and the term of interest is medium term, and you can think of it in 2 ways. It has a form C dagger C S E. And you can think of it, either group it with the atomic term, and then it looks like a light shift on the atomic states of a photon. You basically add this term to H bar omega A, and then you say there's a light shift proportional to the photon number, the text of SE, or you can also think of it as the atom shift in the cavity. So basically, the atom acts as this refraction, and so when group it in the second way, you say H bar omega C is now shifted by an amount that is proportional to this. So either way, you get this effect, and you get this 2. And then what Young worked out very nicely is to formalize this. If you take this Hamiltonian term in the middle and C times C, then you can think of it formally as a Taylor series expansion, and then you get the SC linear term that we don't care about. We echo it out of spin echo, And then the lowest order term is big, that is next biggest one is SE squared mitigated with a spin squeezing. There are also higher order terms, but they are typically very small for system. And so this is formally how you can understand it, and so basically. However, there's also light atom entanglements making the process non-human. So what do I mean by that? You're shining light onto the cavity, and the atoms shift the cavity. That means, for instance, the transmission from the cavity depends on this. So there's information leaking out about the atomic state that is, for instance, contained in the power of transmitted light or in the phase of the transmitted light. That term we don't really want, because that term we are not able to measure the light. If we measure the light, we perfectly backward, but photons have losses, and we typically don't even measure the light field, and anyway lose most of it. So that means that we have an entangled system with atoms of light, and then we are tracing out the light degrees of freedom, and that leads to some dissipation in the atomic system. There's still spin squeezing, but it's no longer what we call unit. It's no longer area research. And so in the early experiment, first experiment, I'll show you some results from Monica's PhD thesis. We understood that this was happening, but we thought, well, the best thing that you can do is partner with slow. Because there the interaction is the strongest, right? This effect and this light is the strongest. Unfortunately, there also this light atom entanglement is very strong. And then again, following our conversation, Monica pointed out a paper done by a Chinese group who pointed out that when you went away from resonance, which seems counterproductive because you're making the SE squared term smaller. So this in red is the strength, this SE squared term, the desired term is the new one. If you go further from resonance, you make it smaller, but the light atom entanglement falls off more quickly than resonance. And so it turns out that actually there's an optimum tuning where you make this light atom entanglement small, and you're becoming near unitary system, and you can achieve largest amount of 100. And so this is the idea. So we will not park on the slope of the resonance, but further away. And then basically, as what I will tell you before, you see this red curve is anti-symmetric about this resonance. And so if you're parking, say, at some tuning, you can create SE squared Hamiltonian with one side of the interaction. And if you simply switch to the other side of the resonance, you can create the same SE squared Hamiltonian, but now with the negative sign. And this is what allows you to do this forward backward evolution time that we tell you about. And so when we first use this for spin squeezing this Hamiltonian, so basically place the atoms in cavity, create a position state, shine in the light, and then we get a narrow state, and then we can rotate the state and look for a state. One here indicates the round given state. Below the standard quantum limit, you see we can squeeze more and more, but we ran the detection limit was about 10 dB below our standard quantum limit that corresponded to a few atoms. You can see that we actually are limited by the detection, and that if we, basically cancel or if we subtract this noise limit out, we could find that we could make much better entangled states, close to 20 dB entangled, or spin squeeze much better than we could actually detect. That's what we confirmed. So it would be nice to have a method that goes away from this. To compare this, are results from 2010, which Monica and fellow graduate student Ian Leroux took in the lab. This was the first method of this kind to use to overcome the standard quantum spin squeezing, and at that time we had about not quite 60 spins. It's gone to a factor of 4 and a reduction averaging. I've seen visiting here many labs, many graduate students working on very hard problems. Monica didn't have, and Ian did not have the paper, I think, up to the end of their 4th year or something like that, and then I had a huge string of papers. So sometimes when you're working on hard things, it takes a while. So this in the beginning we had to understand the systems, but then we very quickly had several results on the spin squeezing, understanding how it works. So, however, these first experiments were done on hyperfine states, rubidium, so they're kind of convenient. Rubidium is very easy to use, but it's not a very good clock. The reason why it's not a very good clock, among other things, is that it's a microwave clock, and it's an optical clock runs optical transitions 10 to the 5 times higher frequency that immediately improves accuracy. So then we basically switch to terbium, where one has a very narrow transition, a state that lives longer than seconds, and try to transfer to the same methods. This is the round level structure from terbium, and if you work with strong sequence, it's similar. You have a broad transition for the first laser cooling, narrow grid transition, 180 kilohertz wide, that one can use for further cooling the optical trap. And this is also the transition that we use for spin squeezing, which is part of the cavity of this transition. And then there's this ultra narrow clock transition that we can use to create superposition states and measure time. And so basically what we do is we first create spin squeeze states between the nuclear ground state sublevels minus 1/2, like I showed you before, on this 1/2 clock transition. And then we take this spin squeeze state, indicate ellipses here, and transfer them to the clock state to start our Ramsey sequence, and then we measure the full Ramsey sequence. And this is one way to think about this. We start with all the atoms one states. So the violet or pink blocksphere indicates the levels, the nuclear ground states here, up and down in the ground state, whereas the yellow blocksphere indicates superposition states between one of the ground states and the state that oscillates at 10 to the 15. And so basically we start by pumping the atoms to one of the states, the block that will be up. We then apply a magnetic field, pi/2 pulse, to rotate the states into the plane. And then we apply this squeezing light inside the cavity, which creates this sheared state that is now narrower and close to unitary evolution. And then we rotate this direction of the state so that it's maximally sensitive to the phase, as lowest noise the phase direction. And then we apply this pi pulse on the clock transition, have a Ramsey time, the clock state, and go back down. I mean, I still find it very remarkable that all these experiments, you have the atoms oscillating at 10 to 15 hertz and the laser oscillating at 10 to 15 hertz, and you can measure the phase between them over macroscopic times. Here, for us, even though this oscillation is very, very fast. I think it's just model of laser technology with that. And then basically for the readout, we map back another pi pulse, the state back to the ground state, and then we measure the phase. And so these were our results. We did this for different Ramsey times indicated by the different colors. And then basically we were limited by the coherence of our laser. All these systems, the atoms are much more coherent than the laser. And so any noise that you see between the atom and the laser is always the laser's fault. It's always the phase of the laser changing. Our laser was not very good, maybe between 10 and 100 hertz at the time or so. So we could only do a relatively short Ramsey time of maybe a few hundred microseconds. But we could see that compared to a coherent spin state, which is shown in blue, and the dashed line is the best we could do with an unentangled state for the same atom number. We could see that we could reduce the noise in this case by about 4. And so this was the first entanglement of transition. In the meantime, people have done entanglement both in cavities. So the EDA has an experiment, similar in strontium, similar levels. And then several groups, including Monica's here, and Adam Kaufman, Anton always have also used Greenberg interactions. But as I told you before, we are really limited with these experiments too. We could make much better entangled states than we could measure. So the question is, can we improve on that? It's kind of a waste to make this beautiful highly entangled states and then we should be. And to improve this, we basically reread carefully this paper by Emily and Monica, and let's get his first name, where they proposed a method which we call time reversal. It's called the action-based readout, and that one goes as follows. You start with the state, you you spin squeeze it, and then you imagine for now just displacing by rotate it vertically, and then phase displacing, imagine just displacing the state. Because the state is so narrow, a very slight displacement in this narrow direction will create an orthogonal state to the original state. And now if you're able to do the minus h Hamiltonian going backwards in time, then because these two states are orthogonal and they're following the unitary evolution, when you go backwards in time, the states can also not overlap. They have to be orthogonal. So the lowest order you get displaced coherent state. In practice, you get both displaced and somewhat tilted state, but most of the information is displaced. And so in this method, you see the measurement resolution is no longer necessary to resolve this narrow axis of the spin squeezing, because now you get an amplified phase. Basically, this small phase displacement here, or small angle displacement here, results in much better, much larger angle displacement here as you go backwards in time. So you now only need to be able to resolve the coherent state bit, and we can do 10 dB. So easily resolve one next noise coherent state. There were a few other experiments that used the same idea. And some of them, they did not switch to Hamiltonian. This is from Marcus Oberthal's group. They used both Einstein condensates. Another way to make spin squeezing is collisions between the atoms. Condensates, where all atoms collide with all condensates. These are beautiful experiments. In metrology, they're not great because typically in a plot you don't want collisions, right? Otherwise, you have all kinds of problems with line shift and so on. But as demonstration experiments, they're very nice. And here, they didn't switch the sign of the Hamiltonian, but they put it in a three-level system. So it basically phase of state, making an active spinning with the amount of this Hamiltonian. Mark Hasevich's group also did a beautiful experiment along a similar idea. Again, they didn't switch the sign of Hamiltonian, but they were able to switch basically the signs and have something very similar. Two states that are displaced by a little bit along the narrow axis get displaced by much more. Displacement gets amplified in this direction. And more recently, John Bollinger's group is similar finds, where they use finds connected the spin not to photons like we do, but photons in the ion crystal, which have a similar type of forward map. The way it would look is shown here in this illustration is the Young wave. So basically, start with spin squeeze, you look towards it, and then so you see that the state spin squeezes gets narrow. Now it gets this displacement. Now we evolve it backwards in time, and you see how it becomes displaced a lot more than was originally displaced. I'll show you. So, for instance, here we increase the spin squeezing time, and we're measuring the long axis. You can see that the state that starts out Gaussian, here Gaussian increases squeezing time, develops this other structure. Basically, here the state is squeezed all the way to the poles, or anti-squeezed all the way to the poles, and that's why probability builds up. So this is the forward evolution of the Hamiltonian. And then, however, if we apply a negative sign and then go backward in time, we can recreate the state or the Gaussian envelope that's a little bit larger. Here, state even for the large amount of spin squeezing that you see, right? State for essentially all the way up. And so, if you now measure the simplification of the phase, what is shown in these graphs is the as a function of the signal displacement, the small displacement along the narrow axis, the resultant displacement along. When we go backwards in time, effectively, and then measure the displacement, you see the solid line is shown, and you see visually already a much larger. So the phase that was applied was really magnified by the system, and this is for various amounts of squeezing. So you can see there's quite a bit of difference, quite a bit of difference. And so if we use this method to measure phase, then we go from the standard quantum loop over here to this curve down here, which is 15 times greater. So that means 15 measurements with an unentangled coherent state can be replaced just by a single measurement of the entangled state going forward and backward in time to really achieve the same result. So this is, I will show you the graph for this slice, but this is now substantial. So this graph shows on logarithmic plot the horizontal axis the number used in the system on a logarithmic scale, and the vertical axis is the metrological gain. So that's also a logarithmic axis. This plot, the way it's plotted, the standard quantum is right here, so it's basically normalized to the corresponding atom number 1 square root of it. This region here is forbidden, so you can at best be at this limit. This is the so-called Heisenberg limit, where your resolution increases not 1 over square root of n, but 1 over n. And then this shows various experiments in the system. There are ion trap experiments, which can be quite close to the Heisenberg limit, few ions, so maybe 8 ions or so. And then the record is up there. Mark Krasovich and James Thompson had similar results. Mark's was a little bit better, close to 20 times string squeezing in large systems, also full high absolute resolution using 5 to 6. The red data points show, and these were done by this squeezing by measurement. The red data points show for us, as we varied the atom number and did the forward backward time evolution, that we improve proportional to the atom number, which is sometimes called Heisenberg scale. So we have fixed distance to the Heisenberg limit of about 12 to 11 dB. So there are several contributions. You know, we would like to push the Heisenberg limit. 3 dB comes from the fact that was already pointed out in Monica's paper. The best state that you can use is a super GFC state. It's atoms, all atoms up plus all atoms down. We are using effectively a state, ideally a state at the equator. And if you did take a state at the equator, you would 3 dB worse than the GFC state. And then some other factors from dB atoms. Contrast loss, a little bit of total scattering, free space by the atoms that we do the revolutions. Nonetheless, it looks quite promising. We believe that we were limited by how many atom numbers atoms per load at the time. We believe that we should be able to go maybe 1 order of magnitude more following this line before we start probably or before other various things. Nonetheless, people are actively working on it, and you know, 20 dB record from Mark Krasovich, depending on whether you exclude measurements noise or not. So finally, let's go back and look at this this method of time reversal and ask ourselves, you know, was it really necessary to spin squeeze? So I presented this picture on this paper, which is basically spin squeeze Hamiltonian going forward, displacing going backwards, so you get this amplification angle. But if you think of it in a more conceptual way, right, even if you create a very strange looking state, as long as it has a lot of structure and phase space, and here a small displacement, at least along some directions, will create an orthogonal state. And so basically then if you go backwards in time, if these states have a certain distance from each other, then and are orthogonal, then when you go backwards, they have to be. So we could, for instance, imagine states where you know that are not only sensitive to more sensitive than independent atoms to noise in one direction, but we could even imagine states that have special shapes that are sensitive. So let have more sensitivity, 2 dimensions. And also it seems like in principle you should be able to use any Hamiltonian that creates a lot of structure in phase space. A lot of structure in phase space, we often call that lots of Fisher information, lots of information. Zeyang came up with this, where he argued that start with a coherent state, and you can do this evolution. You can think of it as an entropy, and then we try to generate the state of high quantum Fisher information. Then we displace the state by a little bit, and then we go backward in time, which results in displaced the original state, and then we can just measure, for instance, the distance between this and that state. So that's kind of the metrology viewpoint. But also there's a viewpoint related to information scrambling. If you took a state, you wanted to very quickly scramble the information many degrees of freedom, would also create a state of high quantum Fisher information. And then how would you verify that? Well, you would look at when you displace it, how much does this state overlap? And this is this idea of all-time order correlators that people invented to talk about quantum chaos. Right? What does quantum chaos mean? It means that small displacements somehow exponentially. And so you see there seems to be a very natural connection between quantum metrology and quantum information scrambling. Indicates that maybe a broader class of Hamiltonians, maybe those that scramble very well, can be used to also make states of meteorological elements. And so Young also proposed to use this kind of Hamiltonian. So this is the one that we've seen, the without spin Hamiltonian, but you can add a rotation about the x-axis to it. Even if it seems like a very small change, actually it's fundamentally different because they are, depending on how you rotate, in which direction and at which speed, you can turn this one axis twist Hamiltonian that where the squeezing increases linear in time into a small two-axis twist Hamiltonian effectively, where the squeezing increases exponentially. And for that, you have to basically tune your rotations relative to the strength of the spin squeezing Hamiltonian to a particular value multiplied by 0.5. So let me show you what that looks like. So if you start with a coherent state and you rotate at some speed which is outside this window, then basically what you see during squeezing is the state squeezes and rotates at the same time. So you see it gets narrower, develops some structure, and then the structure gets a little bit less and a little bit more and so on. So yes, it is squeezed, it is entangled, indicated also by these blue regions, negative regions of the Wigner function, but it's not really dramatically changed. And this is because the rotation was chosen not to be at a critical value. However, at a critical value, so up here, the evolution is very different. And this is just a slight change by effect of rotation speed. In this case, you can see that the state very quickly squeezes along the diagonal axis. For the axis, like two axes twisting in the beginning, and then it develops enormously much in principle quantum structure. Now, not of all this structure is accessible to us because we still have some decoherence, some light entanglement, there's some scattering in free space, there's still a little bit of Fisher information leaking out about the atomic state, but it indicates that this state, that this Hamiltonian generates squeezing or entanglement Fisher. And so when we compare this, say versus the evolution time, these gray data are the quadratic, one axis is Hamiltonian, and then the red data are the exponential one. Here's the inset showing on exponential scale. Maybe it's not, it's clear that it's faster. This will be the perfect exponential curve, and then here's when we include this dot dash curve, this will be include these various impedance mechanisms. So it scales close to exponential, but not. And so we can also measure basically the overlap of the state when we evolve backward in time with quantum tomography. So this is kind of a quantum scrambling approach. We initialize the state being unentangled. We use this Hamiltonian to scramble the information. We then encode a small displacement of the state, and then we go backward in time. And then we can do quantum state tomography, basically measure the phase space distribution of the block sphere, and this is what we get when we didn't displace the state in the middle. This is state equals 0, and you can see we get this displaced and slightly distorted states when we apply displacement. So we can also perform quantum state tomography, and then want to look what does the overlap look like between the displaced state after the full evolution and the initial state. And so when we now plot here on the logarithmic axis as a function of squeezing strength or squeezing time, and the system varies quantities. For instance, we can plot the anti-squeezing. This is how quickly the state gets much broader than the coherent state, where coherent state is more or less to 1. Or we can plot the out of time over correlator, just basically this overlapping after the full evolution. So that's a measure of quantum scrambling. Or we can plot the meteorological gain. Then you see that they all follow this exponential inverse curve up to a certain evolution time, and then the meteorological gain starts to drop. This is simply limited by the fact we still have decoherence. But you can see from this that basically up to this time or so, we're using all the quantum information available, which is measured by out of time correlators, basically nearly after that time. And this is our Hamiltonian that uses structures. So kind of brings up the question, could you come up with more better Hamiltonians that produce complicated structure, states of large Fisher information, and more quickly and or more robustly in the main technology. So I view this a little bit as a new paradigm where you use some time reversible Hamiltonian with often cavities, and cavities is simple, but may also be possible to engineer this for locating sequences in other systems. So you scramble the information in some way that stays sensitive to phase, angular displacement. After you create a state, you perform either the angular displacement directly or a random sequence, say, time, and then you fall backward, and then the small phase change in the middle gets amplified a lot, and it's easily released. This is, for instance, also relevant, say, in experiments. Mark's experiment chrometry, where the atoms often expand out of the cavity, and it's very hard to measure far below the standard quantum in the free space. But with these methods, as long as you can do the other things, you can then basically measure something, measure an amplified large space. And this works even for quantum states that have no reduced variance. I will show you that, but basically we can see that we can get an improvement methodologically even for states that have no longer reduced variance compared to the previous. The variance might be quite large, but the state has still a lower structure. It's very sensitive. And with this, I will like to bring up just a summary slide. Thank you for your
questions. Okay, I was wondering sort of this picture of it. If I choose the component, I could do something that's maybe not all scrambles faster. Is there a sort of picture of what observables I can then sense precisely? Like how does that relate to the thing?
That's a very good question. I don't really know full answer to this, but it does seem to imply that, for instance, like you do, you know, by rotating certain parts of the state, like the state sensitive to certain kind of operations, certain kind of change from others. Very roughly speaking, if you don't do rotation subsystem, basically anything, any direction where you get these fringes in the different states, which I will bring up now, where small displacement of matter are sensitive, you know, then there's some other rotation. So you can, if you the Taylor states that are sensitive to particular observables and are very robust. I didn't show you the data here, but usually people think, oh, entanglement makes states very fragile. And that's true, but entanglement can also make states very robust. So if you have a large anti-squeeze in some direction, you become very insensitive along that direction. So it's and so that's an interesting question to, I think, indirectly explore.
In the time reversal scheme, how robust is it to maybe like a slight imbalance in the photon number between shearing forwards?
That's a good question. So theoretical limit assumes that we only photon shock noise limited. So we take, you know, we are careful to control that. We also work with not that large photon numbers, so photon shock noise is pretty large. The other tricks that I didn't mention, but it's not super robust by itself to atom number calculations when you load the atoms. The way we do it, so we use, for instance, a trick where instead of using one color like I've showed, we use two colors in a certain ratio so that we get quadratic instances. So these are actually the bigger problem.
Is there a simple reason why the amount of squeezing for the 1x6 state model was larger than the amount for the like LMG model?
The amount of
Like you mentioned like 60 dB squeezing for the like LMG Hamiltonian versus the 1x6.
oh yes, that's a very good reason. So when we did the normal spin squeezing on the Hamiltonian, we optimized the tuning. I showed you this curve to minimize the information system. And that was easy to do because the state squeezes horizontally and we're only measuring SC. And so all the time we always gave the same amount. We didn't understand the system very well, or we didn't think of that for the LNG Hamiltonian. So the ideal LNG Hamiltonian would actually use a different tuning and possibly a time-dependent tuning. to minimize the light action. And that was not done. That's maybe something to go back to. Yes.
So you made this comment that you can tailor expanded powers of SD. So I guess one question is, it seems like if you parked on opposite sides of the feature, you would cancel out the SC squared term. The one question is, how does the SC cubed or SC to the fourth scale with cooperativity, collective cooperativity? 1 and 2, is there any reason that would be an interesting term to look at?
I think it would be interesting because it would deform the state in a different way. Unfortunately, you do it very naively close for resonance, you find that term is substantial. But I haven't looked into details. There may be some optimal tuning where that dominates for all of them.
Yeah, I guess sort of a follow-up to her question. So it does seem like there's a connection between sort of what space you scramble in and which observables you're sensitive to. So if I scrambled in the full many body invert space, I guess I wouldn't be very sensitive to, say, local rotations. But I'm wondering if also, I guess, within that space, should I just think of it as an equally sensitive to kind of maybe all perturbations that keep me in that space, but I also can't distinguish which. Can I distinguish? Like, can I distinguish which direction I wrote?
I think you can distinguish, for instance, if you imagine having star-like, instead of a political uncertainty, some star-like, which is, for instance, the energy Hamiltonian, right? Then it would be sensitive to 2 directions that are orthogonal to one another. And they would result in 2 different displacements.
I buy that, but that seems a bit more like squeezing when you're intentionally putting in a particular structure as opposed to sort of making things completely random, right?
Yeah. So if you make them completely randomized, you can, guessing now, you can probably make it sensitive to something like a central spin model. Maybe there's a way to sensitive ways of that spin, particularly. Nothing else. In general, yes, I don't know what the structure look like beyond the fact that you can see kind of the basis that you can have distributions where you're sensitive along 2-3 directions and not along others. Maybe you have.
Maybe I'm just hesitating about whether that should be called scrambling or whether it's more that I put in as.
Okay, very good point. Maybe for everybody.
Yeah.
We are really here considering the evolution on the symmetric space of the velocity, so we're not working in the 2 to the n inverse space, but only in that subspace. Nonetheless, you can have quantum chaos of certain Hamiltonians even in that subspace.
I think, sorry, I don't want to harp on this too long, but I'm just wondering if the more chaotic it is, do I lose that structure that actually lets me do something like, oh, I can tell whether that was.
I would say for 2 orthogonal axes, it works. For multiple axes, I'm not sure how many methods you figure out.
Great question along the lines of robustness. So do you know where it seems like if you have this chaotic again and then you're reversing it, it seems like you'd be very sensitive to full noise or so I'm wondering if you have an idea fundamentally what the limit is to this type of approach.
Well, I mean, our input to our system is the atom number, which we can separately measure and know. And then the only thing that we put in is photons. As long as we look no fit or short noise, there's no extra classical noise in the system. So then beyond that, everything is done by the evolution. Hamiltonian, maybe the light path. I guess I want to say from an experimental point of view, that light is practical, intensity, right? And then it follows quantum evolution. With the only complicated thing is this light atom. First, but there are ideas of it possibly. But yes, you get more sensitive. Maybe you can design the system clever way that you're being sensitive to noise that you don't want to measure and that hurts you, but sensitive only to the type of noise. If you want to measure, say that you want to measure gradients, maybe it's completely insensitive to common mode noise and only measure differentials.
Along those lines, what about like atomic motion? That seems like it's different in the forward and that direction.
That's correct. So we time our sequence over to the 60 hertz in the lab for magnetic noise and to the atomic vibration frequency. People have seen a little bit of influence of that, so we try to reduce that. Of course.
I guess I'm curious, kind of, with this more general, like kind of time reversal based kind of metrology paradigm. Is there still like a kind of notion of like having like a trade-off direction where kind of in the kind of squeezing case, you squeeze along one axis, but then you anti-squeeze in another axis. If you just kind of apply this kind of very more exotic Hamiltonian, could you imagine somehow like sidestepping that where, say I create like a checkerboard looking Wigner function? So that's kind of high resolution in all directions, but that doesn't necessarily violate the uncertainty principle because the kind of probability mass is still like widely distributed. Is there like still like something we're trading off against, or?
Yes, that's a great question. So the checkerboard pattern, indeed, you would imagine that you are very sensitive to all directions. What you lose is dynamic range. Because if you replace by one full checkerboard pattern, you're back approximately where you were before. So it's a little bit like the GHZ state, you get a lot of phase evolution, right? But that phase evolves so quickly that you know if you have 2 pi of phase, you can't distinguish. So that's the price you pay if this checkerboard example. It's dynamic range, you can only measure, allow for phase changes with much narrower.
I see, because then you'll get kind of perfect overlap and then like very orthogonal and then perfect overlap again.
There are ways, and people have proposed ways to fix that. You'll probably use multiple problems. So that some short gravity time to measure coarsely, make sure you can use fringe, and then more measurement time and more measurement time. That would be
Oh, yes.
Okay, well. Further questions? That's very fun.